Good evening, everybody. It's a pleasure to have you here in my class. So we have a full program, and I hope you will enjoy it. I mean, the talk title is pretty long, and I hope I can get you some of the excitement that I have had during the last 30 years of my life and share it with you. So it's an exciting journey from ultrafast laser physics to frequency metrology and attosecond science. And when I started this journey, I never even thought I'd go into frequency metrology, nor did I think I ever going to get into the attosecond. So, as an outline, I would like to first give you a little bit of a taste, an introduction, a little bit of a feeling. I mean, I cannot go too much into the depths here, just a little bit of an idea how the measurement technique goes and evolves. And then we go a little bit in more depth into lecture 2 and 3 about laser pulse and frequency comb and the ultrafast solid state lasers. Okay? And so let me just jump in and basically give you a little bit of a calibration about the time and time scale and length scale in comparison. So we are starting here with a second and a meter, which is our daily life experience. And then we go always about a factor of 1,000, so from a second to a millisecond, which is relevant for ski racing. Another 1,000 to a microsecond. People still normally can kind of think what this is all about. A nanosecond, a typical switching time of integrated circuits. To a picosecond, which is the oscillation of atoms in lattices or on molecules. And then to femtosecond, where you get into really small molecule movement already in femtosecond dynamics in, for example, semiconductors. And then you go another 1,000, which is then the attosecond, which is actually the movement of the electron on an atomic scale. So we're talking here 18 orders of magnitude that you can cover in your laser lab at a university facility, which you could not do if you would do that in space, right? If you go from a meter to a femtometer, you are nuclear physics. And then, you know, down here is something bigger in terms of the equipment that you need to look at. And then attosecond basically means that's 10 to minus 18 second. The femtosecond time 10 to minus 15 second. And sometimes people think, gee, it doesn't really matter, but there is actually a real application that actually matter for the femtosecond. And you can, and an important, in Switzerland, we just started a long-term research program that is looking at ultrafast processes on an atomic and femto and attosecond time scale. And this is actually NCTR MAST. It involves 16 professor group all over Switzerland and has a period over 12 years to address those fundamental questions, because it is really the first time we can actually resolve the dynamics on the atomic scale with femto and attosecond time resolution. So if you are more interested, if you type in NCTR MAST, MAST stands for molecular ultrafast science and technology, you can keep assure what is going on in Switzerland on this subject. So when you go into this kind of femto and attosecond, the only way you get there in terms of time resolution is with laser pulses. And normally you describe the laser pulse as follows. So all of you know how to write a plane wave that is propagating in Z direction, right, with the fast oscillating frequency component omega 0. And if you go to a fixed position, you have the time-dependent oscillation of expanded in time infinitely, right? And the only thing you do then if you describe a laser pulse is you multiply this plane wave with a time-dependent envelope instead of having a constant amplitude. And this time-dependent envelope is the so-called pulse envelope. And that limits this fast plane wave oscillation over a certain time period, right? And you can make this one very, very short. I mean, this is, for example, a very short pulse because it is comparable to the oscillation period. So at 800 nanometer, one oscillation period is basically at 2.7 femtosecond. So when you look at it, when you have a 5 femtosecond pulse, for example, then you have a light disk which is extended in space of over only 1.5 micrometer that is moving at speed of light through the space, right? A flash of light, which is extended over 1.5 micrometer. It's worthwhile to kind of imagine that, you know, because the speed of light means that the light propagates in 1 femtosecond over a distance of 0.3 micrometer, right? And it helps to keep a little bit the order of magnitude that at 800 nanometer, one optical cycle is 2.7 femtosecond, right? So, so on this time scale of basically going from a microsecond, nanosecond, then pico, femto, attosecond, the first time the femtosecond has been resolved is with ultrafast short pulsed laser physics, and I will explain to you how the techniques typically work. It's based on the so-called pump probe spectroscopy, and that actually allowed to resolve chemical reaction of small molecules for the first time, which was rewarded with a Nobel Prize in 1999. And now we actually got into this attosecond regime, which allows us to actually resolve the dynamics of the electronics movement. And as we know, the electronic dynamics is actually driving the chemical reaction ultimately. The chemical reaction is moving of atoms, but the electrons are responsible for the bonding. The electrons are responsible for the transfer of charge, of transfer of energy. And that's why if we really want to understand how it works, it is helpful to really resolve the electronic dynamics independent of the ion dynamics. So when you look at the application of ultrafast lasers, you have basically, you can group the application based on the properties of the short pulses. So the short pulses have a short time resolution, so it's a short flash of light, which give you a good time resolution in measurement. Then you can have these flashes of light coming at really high repetition rate, which you can use for optical communication, clocking. Then you can concentrate the energy into a really short time duration, which then pushes up the peak intensity. And you can use that for nonlinear optics or material processing. This is one of the fastest growing market actually. You know, lasers have been used in material processing for a long time, but with these short pulsed lasers now, we can do much more precise machining and also machine materials that normally would fall apart, like ceramics or solar cells and so on. And a short flash of light means we have a very broad spectrum, and that gives a whole bunch of application. One of them, which has been very popular over the last couple of years, is the frequency metrology. So let me go a little bit more in details of all of that. So when you look at first in the time resolution, you know, when you go back to Francis Crick, who said 1962, if you want to understand function, study structure. So he's a chemist, so normally as a physicist, what do you really mean? That basically means if you know the structure of molecules, you know, for example, a molecule who has kind of a docking end like this, you know that this molecule, if this one is fitting into this docking end, it can dock in and have a function, block a certain chemical reaction, have a certain healing, whatever, for pharmaceutical application. So this structure actually allows people to develop new medicine. And to know this structure, you need to have the wavelengths that actually resolves the structure over the diffraction. So therefore, people have been building synchrotron light sources to provide the wavelength range in the regime of the structure that you want to resolve. So typically 20 nanometer to angstrom level. the dimension of the molecule of the things. But the synchrotron light sources have not really provided too much time resolution. So it's really static structure. But they have been booked out and have been extremely successful. And just that you know where this is going, when you're talking about 20 nanometer to 0.1 nanometer, that you get a little bit of feeling, this corresponds to a photon energy from the EV regime to the kilo EV. So you really move into the hard X-ray regime in terms of your sources. Now, what you would like to do actually, and what people also discovered, is that actually the static structure alone is not always giving the full picture. Certain things only work. For example, how oxygen is bonding to the hemoglobin is only working in a dynamical process. The static picture would not explain how the oxygen gets bonded. And so in principle, what you really want to ask is, if you want to understand function, study time-dependent structure. But of course, at that time, in 1962, it was impossible to address the time dependence, right? But today, we can do that, okay? And the question is, how do we do this? We basically use ultrafast science and technology now. I explained in a little bit what that really means. But generally, you can say that if you develop new tools that allows you to see processes which you normally cannot see, you will discover something new, which is beyond your imagination. Because sometimes you can theoretically predict something, but if you don't really have taken all the parameters into account, you might not really predict the right outcome. Now, to visualize that one, I want to give you some example. Even in the 1 micrometer time resolution, you will encounter surprises. So normally, if you shoot with a bullet through an apple, it makes bang, and then you have apple mousse on the floor, right? But you don't know how the apple is actually falling apart, right? Normally you would think, oh, well, it's, the apple mousse goes in all directions as far as you can tell, right? No matter where you stand, you get dirty. But actually, if you can time resolve it, if you get the flashlight, synchronized to the bullet correctly, you can take this beautiful photograph and you can see that the bullet goes through the apple and actually it explodes not only forward as you may think, but also backwards. After you see this picture, it actually makes sense. You can explain it, you can model it and understand it perfectly well, what is going on, right? And then another one, like the card, when you actually manage to hit the card from the side and actually shoot through it, who would have thought you end up with this snake line here? Or another one, a bloop into a milk, right? A drop into the milk. It goes in, bloop, and then actually something comes back. And under certain condition, you create this crown. Who would have predicted that this crown gets created? Now, now that you see it, you can actually model it, you can understand it. And now imagine it would be a chemical reaction, and you never even put enough parameters into your model, you never would have theoretically predicted that something like this occurs in the dynamics. And maybe exactly the crown is important to make it work at the end, right? So even in the 1 microsecond time exposure, surprises are there. Then what do you think is going to happen if you move into the femto, into the attosecond? In the attosecond, where we don't even know what is going to happen, right? So how do we now address the time scale, which is going much faster than a microsecond? A microsecond you can do with flash photography, right? You have a dark room, you take a picture with a camera, and the time resolution is given by the duration of the flashlight, right? Which is triggered at a certain time. Now, how do we do it with a laser? So let me take the analogy of flash photography again, where the bullet goes through an air balloon. So I have an air balloon here, sitting here, and the bullet went through this air balloon, and you see it's already huge holes in the air balloon, but you know, the air balloon is still in pretty good condition, right? And you know, how do you do this one now with the laser light? So normally you have a short pulsed laser, a femtosecond or attosecond or picosecond, and one pulse out of this laser is starting a ultrafast process. So in this case, now if you take the analogy to this picture, this first pulse is the bullet, right? It's basically triggering the explosion of the balloon. And then you take a weaker, a so-called probe. So the strong pulse you call the pump, right? Because it starts the process. And then you take, through a beam splitter, a weaker pulse and delay it just through the flight, time of flight, right? You know, distance here of 1 micron gives you 2 times 3.3 femtosecond. Mechanically, you can step a fraction of a micron, very well controlled, stepping through, right? So you can control with a fraction of a femtosecond the delay of this second pulse. This is the probe, which is the flashlight that is looking how this device under test is behaving. So at this point now, if I take this analogy with the flashlight, this would be my flashlight, right? Now, if I then step through the delay here and take a later delay, then the balloon is already, you know, falling apart a little bit more, but you can see it's still together. And then a little bit later, the balloon is pretty much into pieces. But the amazing thing, when you look at this one, the form of the balloon is still maintained. And now you can imagine if this would be a molecule. Of course, a molecule falling apart, you can basically dissociate the molecule with a laser pulse, right, to make it fall apart. But you cannot see it anymore with flashlight. So you need another visualization of this structure. And one way to do it is through, for example, diffraction. So if you do this pump and probe, so the first pulse has the right wavelengths to dissociate, for example, this molecule. And with the second pulse, which is an X-ray pulse, it can resolve the structure of the molecule. And you can actually then step through how this molecule is falling apart, and you can model it, right? So this is basically a standard technique that is being used for ultrafast spectroscopy. It's called the pump and probe. And you can then have any variation how you measure this one using different visualization of the device under test that you want to look at. And there is huge amount of opportunities, and a lot of things have been measured over the years. Okay, so you can actually look at chemical reaction, you can look at magnetic properties, you can look at nanostructures, you can look at biomolecules. It's a huge variety. Any surfaces, catalysis process, anything. It doesn't have to be just diffraction. It can be an electro-optic effect. It can be a magneto-optical effect, etc. So it's a huge variety of techniques that can be used. But normally, if you want to do it on this structure, to resolve the structure, then of course you need to have a wavelength which is comparable to the size of the atoms. And the only way to get to that is into the soft and hard X-ray regime. And that's why, to get the time resolution of these dynamics, people build all over the world these so-called free electron lasers, because they in addition to getting the soft and hard X-ray regime, they also get you the time resolution. Okay? And for example, in Switzerland, we're also building one. The one that is operating right now is at Stanford, and more will come online in the next couple of years. And as I said, the resolution will be of these free electron lasers, typically in the femtosecond, and the wavelength regime and the spatial resolution will be in the soft and hard X-ray regime. Basically a wavelength of 20 nanometer to 0.1 nanometer, basically an angstrom. So what can we do at the university lab? I mean, a free electron laser is not something you can have in your university lab. So typically at the university lab, we can have ultrafast lasers in the UV, in the visible, infrared, in the mid-infrared, in the terahertz regime. This is all things that we can get readily can have in the lab. We can get them down into the few cycle regime so that we only have 1 to a few cycle per pulse. But the wavelength is, of course, not sufficient for diffraction measurement to resolve molecules and so on. So you need to resolve different optical properties to get the dynamics out of these measurements. Over the years, basically, people have discovered the so-called high harmonic generation. And with the high harmonic generation, using, for example, the infrared of these ultrafast lasers, amplified infrared pulses, we can actually get up to 100 EV and potentially into the 100 attosecond regime. And these are, this is, for example, a source that we build up at ETH that allows you to get pulses in this 100 attosecond regime. In that regime, the pulses will be absorbed in air, and that's why everything has to happen in vacuum. So you reduce your laser table space into the space that you have here under vacuum. So to have these containers here is just, having some flexibility when the laser goes in here to set up your experiments, to do these pump probe experiments, because they have to be in vacuum. So you can arrange it over the full laser table, because we cannot, obviously not really work in vacuum, right? So, and then through all this work, we discovered more recently the technique which we refer to as the Attoclock technique. And with the Attoclock technique, we've been able to actually resolve the fastest processes in quantum mechanics, such as, for example, the tunneling delay time. And the Attoclock technique will be a topic of the plenary talk tomorrow morning. So after this master course, you should be then able to understand those experiments better tomorrow. So let me go now a little bit more into the application. So it's clear, good time resolution. The shorter your laser pulse, the better is your time resolution. And that's why it was clear for all these years we just tried to get shorter and shorter and shorter pulses, right? Because every time we had shorter pulses, we got better time resolution in the measurement, right? Yeah, just interrupt.
So according to the Heisenberg principle, the delay in uncertainty principle also, if you have a shorter time, then also
the spectrum becomes larger.
How do you solve that problem?
You always have to be, the optical spectrum becomes larger, right? And then it depends on your measurement. What are your observables? And how do you define the time resolution? And the Attoclock is, for example, something where you can actually get very good time resolution without attosecond time resolution, without actually having a problem with the Heisenberg uncertain principle. So come tomorrow morning. So it's always a question, right? What you measure in quantum mechanics? What are your uncertainties, right? What are your observables? I only gave you now a very simple group of type of experiments, which is this pump probe type of experiments, but there is different variation of experiments where you also can get time resolution. And one of them is the Attoclock, for example, where you actually work even with femtosecond pulses, which is amazing too. Yeah?
So you have a very short step, but is it a problem that you have all these mirrors and all of them are vibrating? And,
how to get the pulses really short?
no, it's okay. I understand that.
Aha, to do.
Yeah. How do you solve this problem?
Okay. Normally, for example, the attosecond, you really have to be very careful, but in the attosecond domain, you're in vacuum anyway. And when you look at the picture of the atto line, look at this. Here, it's on a laser table, And we actually put on top of a laser table a plate which is thermalized, so that you really have the interferometric delay line which is in the sub-femtosecond regime. And with this one we have 100 attosecond time resolution, and you can get it that accurately. But you have to take care of it, right? Because you average at a certain delay for a long time, depending on the measurement, and you have to keep it stable. Otherwise, your time resolution is washing out. That's clear. Yeah, absolutely. Good. So good time resolution, the short pulses, but there is, of course, a lot of other possibilities. I mean, in principle, it's your creativity that allows you to come up with new measurement technique, how to get good time resolution. And it's actually funny, the Atto clock we could have done long time ago, but we simply didn't have the idea. And it's actually only through, detours that we came up and basically created the Atto clock. But more of that tomorrow. So the other one is, what you can also get out of these lasers is pulses at a really high repetition rate. And this is basically being used today. So, I mean, you couldn't go onto your internet without actually any lasers. And, when you look at how the optical communication is going, I mean, everything is growing, more and more bandwidth is going. I mean, this is still growing exponentially. And it's clear that we will go up in repetition rate from the gigahertz towards the terahertz in terms of the optical communication. So we use it in long haul. And normally you use photons, light for communication, and electrons for switching. Why? Light is not interacting very strongly, so it's great for communication. Electrons are strongly interacting, so they're good for switching. So that's why I think it's a good combination. It's moving. Optics is moving into the optoelectronic devices. So we already replacing electrical cables. So this is in a data center. The data center becomes more and more, you need to have a nuclear power station next to the data center, right? And that makes them not so popular after all. And when you look at the electronic cables here, it's a mess, and already just replacing this electronic cable with optical cables, you already get much cleaner interconnects. And it's also clear, today already optics is down on this level, but in the future, optics will move inside the computer as a communication between the boards and between the chips. Already today we have multi-core microprocessors, and if we want to use, and they will move to hundreds, thousands of cores. And if you want to use these cores for parallel processing, they need to process in synchronization, right? And one way to do this is with optics between the two. And so I think this is clear that the optics is also moving into the computer, into the personal computer from all of us. So the high peak intensity, of course, if you have such a high intensity, you ultimately burn a hole, drill a hole into any kind of material. And there has been a lot of studies done, and you can do actually more precise material processing when you get into the shorter pulse width regime. And the reason, the idea is it's called ablation, basically means when you come with the long pulses, you have a tendency to melt the material, and it melts, it gets injected like a volcano type of thing. You have to put in more energy, whereas when you work with short pulses, you can work with less energy, and you evaporate the material at each shot. And so it's a much cleaner, less heat load on the device, and so you can actually cut through glass, through ceramics, and any kind of critical material. There is no iPhone that has not been touched by an ultrafast laser today, right? So you can do a lot of extra things with additional things with with ultra short pulses. You can be more precise, you can get better high surface quality. You can get functional surfaces that either, you know, make the water attracted or rejected, or you can have material processing inside the material given by the focus, and only at the peak power something happens. 3D printing in the micrometer regime, so not just macroscopic. So there is infinite possibilities with this kind of laser. And this is one of the fastest growing market out there in industry. And you can just think, I mean, you're getting very close to the holodeck where you say what you want and it gets produced in front of your eyes, right? So we're getting closer. And then, of course, the other things is that the short laser pulses produce a very broad spectrum. And the broad spectrum has a short coherence length for interferometry, and that can be used for OCT. So you can actually look into your eyes, and just to get you a feeling, this is basically the resolution of the retina looked with a Ti-sapphire laser pulse, 30 femtosecond, and the optical spectrum of a 30 femtosecond laser pulse that penetrates a little bit into the material and gets partially reflected. And this is the spatial resolution that you get. And with a 10 femtosecond pulse, you already get a much better resolution. And so you can actually resolve if actually your retina gets detached at a much earlier position and time. The spectrum that you could get from a mode-locked laser can be extremely broad. Through nonlinear processes, you can make it cover the whole visible spectrum, so the light becomes white if you go through a nonlinear process. But the amazing thing is, if you look very closely, actually when it comes from mode-locked laser, then it is not continuous, averaged over all the pulses, and I will explain that afterwards in the next lecture. It's not continuous. It actually has a line structure, and the line structure is equidistant, even if you have dispersion in the laser, which is actually also maybe something not so obvious, right? And so a mode-locked laser actually produces a ruler for the frequency, because you have over the full spectrum, you have each individual lines. They are equally spaced, and they're equally spaced with an extremely high accuracy. And this spacing can be used to actually then build optical clocks. So let me just very quickly give you an idea why an optical clock is more accurate than, for example, an atomic clock. So how are clocks defined? A clock is basically using a periodic motion, and you define how many repetition of this motion happens per second. So in the slowest, say, 1, this is a second, right? So, and of course, and then you just count this movement, and this is how you define the time. So the faster this is swinging, the smaller is the error on a fraction of the count, right? On say, you make an error of 1 count over an hour or over a day, right? So the faster this is oscillating, the smaller is the error. So when we went from the sand clock to the mechanical clock to the quartz oscillator, we made a huge progress in the accuracy of our watches. I mean, the quartz oscillator basically oscillates at 10 megahertz, and we just count this 10 megahertz oscillation, in which we can easily do. And then the progress was then to go to the atomic clock, which is actually oscillating at 9 gigahertz. 9 gigahertz we still can count today at gigahertz, right? And that's why these atomic clocks are so accurate, and all the satellites actually use atomic clocks in space, and the GPS would not work if we wouldn't have these accurate clocks up there, and we would have not, GPS also wouldn't work if Albert Einstein's prediction in general relativity theory, we would have discovered general relativity theory with GPS. If Einstein wouldn't have done it for us earlier, right? Because then our measurements always would have been off, and we would have tried to figure out why is it off. And then we would have discovered the general relativity as well, right? But the engineers would have discovered it, right? But Einstein was actually a little bit ahead of the engineers, but it was part, you know, without that, the GPS wouldn't work so accurately. So what is the optical clock? The optical clock is basically that we take optical light. Optical light, what is the frequency of the optical light? It's in the hundreds of terahertz. Hundreds of terahertz we cannot count anymore. There is no electronics that can count hundreds of terahertz. Right? The fastest electronics are in the terahertz regime, you know, really good university records, right? But nobody can count in the 100 terahertz. So basically you cannot use the optical frequencies as a fast oscillating to define the time. And with the frequency comb, basically you can count, because you have this frequency comb over the full visible spectrum, and then you take this unknown frequency that you want to count, right? And you just do it as a beating, right? I mean, if you have then a photodetector and you have this unknown frequency beating with the frequency comb, it gives you a measurable signal at basically the beat signal, which is the spacing of the frequency comb. So if the spacing of the frequency comb is in the gigahertz, you can count, right? As long as you know the ruler really well. And this is how do you know it and how do you stabilize this frequency comb? I will explain that in the next section. But this is basically why the optical clock's going to be so much more accurate. And the hope is that with the optical clocks, you can actually measure the wave that hit the UK beaches, because they have a very specific frequency, and the gravitational waves from these waves you can hear. I mean, you can measure in Paris with an optical clock. Okay, so, and the idea is that hopefully, maybe with the optical clock, we can actually measure at one point if or our natural constant are actually constant over time. And we do a measurement where we stay still alive during the measurement, right? If the natural constants are constant. I mean, why should they be constant? We don't even understand them, where they're coming from, right? So, then moving to Attosecond. So moving to Attosecond really changed life. For a long time, you know, we were stuck in the few femtosecond regime in terms of the fastest time resolution that we could achieve with any means. So in the mid-80s, the shortest pulses were produced 6 femtosecond in Chuck Shank's lab at Bell Labs. And that pretty much remained. The technology improved. We got the 6 femtosecond easier and easier and easier over time, but we didn't get much shorter. The breakthrough really came with the attoseconds, and as so often in laser physics is that it came as a total, I mean, it was not, oh, tomorrow I'm going to discover attosecond. No, it was kind of, again, by having lasers, having tools available and just shooting into something and see what is going on. And the people who actually have all their eyes open and also look for the unexpected are going to see something and hopefully can explain it. And that's how the attosecond science actually started. So in the femtosecond and picosecond time domain, we can today easily produce these pulses from laser oscillators. I mean, you can get into the few cycle regime, you can buy these lasers, you don't even need to build them anymore. And there is even industrial applications of this time domain that are now emerging and are becoming very strong. And then the next frontier is this attosecond time domain. To really support this short time resolution, you have to move up into the VUV, XUV regime. You need to increase your frequency. You need intense femtosecond pulses to get there, and you generate it through this highly nonlinear process, which is the so-called high harmonic generation. So, you know, remember I told you a short laser pulse is shown here at 800 nanometer. The optical period is 2.7 femtoseconds. So you cannot go much shorter than an optical period, because then your optical spectrum goes, you know, DC. At DC it stops, because DC doesn't propagate, right? So you have a finite optical spectrum, and that basically limits your pulse duration to the femtosecond regime. If you want to go to attosecond, the only way to do that is to move up in frequency to shorten this period, right? And the way it was done is basically high harmonic generation. The first person who really saw the so-called plateau in this high harmonic generation was Anne Lullier in 1988 in her paper. So basically today what we are doing, we are taking an intense infrared laser pulse, which is typically based on a Ti sapphire laser that produces 5 to 30 femtosecond pulses with enough intensity so that when we focus it into a gas jet like neon, argon, xenon, with a peak intensity of about 10 to the 13 to 10 to the 15 watt per square centimeter, the nonlinear process is so strong that we not only produce second harmonics, third harmonic, and so on. No, we're producing many, many harmonics, and we're going up to actually hundreds of the original harmonics. So we're going from the infrared, 800 nanometer, 1 micrometer, and we move so in the 1 EV regime, and we're moving all the way up to 100 EV. And you know what was surprising is normally when you do nonlinear optics, the efficiency goes down because it's a nonlinear process. You do a Taylor expansion, perturbation theory, and you expect that the efficiency goes down, right? Every higher order will have a lower efficiency. But the surprise was in the experiment is that there suddenly was a plateau. And this plateau was basically first discovered by Anne Lullier. And this plateau was an equally spaced frequency comb that went over time all the way to 100 EV. And then, of course, anybody who knows about mode-locked laser, if you have an equally spaced frequency comb, if you take the Fourier transform, you actually, and if this is a coherent frequency comb, you produce attosecond pulses. So early on, it was predicted that there should be something attosecond in there, but you know, for the longest time, you couldn't measure it. I mean, the generation was kind of there, but there was no way to measure it. And actually, measuring attosecond pulses was the first experiment that had to be built up and actually designed, and the concept had to be made. And so what you can easily get in the lab today is this plateau all the way to 100 EV. People are moving of trying to push it further into the hard X-ray regime because of the diffraction, right? I mean, that I talked about in terms of the motivation. But the efficiency just goes down more and more. I mean, the typical efficiency from what you're getting in here, this is at about 10 to minus 6. Right? But you start with so much that you still have enough photons to do experiments. And how is over time, people learn to explain how it works. And it was then until 1993. So you see, the first plateau was basically 1988. People said, why is this possible? Why is there a plateau? People did not understand. And over time, came an explanation, and the three-step model is the simplest way to explain this process. So you have an electron in an atom like neon, argon, right, noble gas, and you bring in this really intense laser pulse. So the electric field of your laser pulse bends the Coulomb potential, every time, going through the oscillation. So it bends the Coulomb potential, and because the electric field is so strong in this short pulse, that the Coulomb potential is so strongly bent that the electron can tunnel out, and as soon as the electron is out, it gets accelerated and then stopped at the turning point when the electric field is turning around, and then gets accelerated over the full half period, slammed back into the atom. And if the timing is right for this electron coming out here, it can get a lot of energy. It's kind of like the slam shot, where you let a ball land and then yum, and you yank it back. So not all electrons come back. So depending on when the electron comes here, you get different final energy. And so averaged over many of these processes, you can cover the whole energy regime. And you have a COM, because this is a periodic process. Every half a cycle, the electron gets driven back, the next half a cycle. So the spacing of this frequency COM is basically 2 omega, right? Half an optical cycle. So it gets back, then you have the overlap, spatial overlap, and the electron can recombine and emit an XUV photon. So it basically means when you have a longer pulse, you can actually get then a pulse out every half cycle. So, and if you assume that this frequency COM is coherent, and you would Fourier transform it, it's very similar to mode locking, and you get a short pulse depending on how broad your spectrum is. And so you can easily get an attosecond pulse easily, conceptually. If you can then deal with it and measure it and use it, that's a different thing, right? So assuming you have now a long, strong infrared pulse, this half cycle is happening many, many times, and so you get in the time domain many attosecond pulses repeated at half the optical cycle. So at 800 nanometer, optical cycle is 2.7 femtosecond, so every 1.35 femtosecond there is a pulse coming. And for pump probe, this is really fast, right? There's not too many experiments that you can measure where you can just hit the device that you want to measure, with a certain delay so fast with the next pulse. Because normally you want to hit a fast process, and the fast process takes some time to evolve. And then comes the next pulse. So 1.4 is very often too fast. And so that's why for many applications you would like to have just one attosecond pulse, and then for a long time nothing, and then again attosecond pulses. And so if you actually take the pulse and make it shorter and shorter and shorter, and then you only reach the threshold for the tunnel ionization and going back actually only during one optical cycle, then you can actually restrict this recollision process and the single attosecond pulse generation to 1 per femtosecond pulse, right? And then the repetition rate of this attosecond pulse is given by the repetition rate of this strong femtosecond pulse, right? And so for many experiments, you actually would like to have that one. But this requires that you have these really high intensities of the laser pulses with really short pulses, which is not easy. So normally the short pulses, when you look at how it evolved over time, the first time, the femtosecond pulses were produced were with so-called dye lasers. And the whole time, the first chemical reaction dynamics and all the original pump probe experiments and so on were done in the 70s and 80s with these dye lasers, which was very hard to work with, right? And the breakthrough really came with the Ti-sapphire laser, because with the Ti-sapphire laser we finally had a solid-state laser available that could produce, that had the necessarily bandwidth, and that could produce your short pulses with much more power and much more ease. So in the morning you can just switch on this laser and then go on and do this experiment. Whereas in this dye laser area, it was much harder to work with. So for the attosecond, however, you need to then amplify these laser pulses. Out of a laser, you don't have enough power at this point. I mean, we're working on it, of getting this done. So normally when you amplify, you know, the breakthrough to really high intensity, to the millijoule regime, or even much more, of course, is the chirp pulse amplification. So you take the femtosecond pulse and first broaden the pulse so that the peak power is not so large that you start making a hole into that you don't micro-machine your amplifier, right? So you reduce your peak power, amplify, and then push it together again and get your short pulses. And we will discuss that in the lecture 2, how exactly this is being done. But then, of course, you have normally much longer pulses than you started off with, because any amplification, you have gain narrowing, and you have a much broader pulse afterwards. And then you have to, again, find ways how to compress it. And there have been different techniques that have been developed. I mean, one easy way is through filament compressor. So you just go through some gases again and produce a broader spectrum that you can then compress again. But you know, I cannot go too much into the details, but you can get now with different techniques back to the 5 femtoseconds through an additional compression. So you can't just amplify and then hope that you stay at the 5 femtosecond. You have to compress it again, because the amplification, unfortunately, is broadening your pulse. So these infrared pulses are then used to get the attosecond pulses. So that basically means, in comparison to the femtosecond domain, in the femtosecond domain, you know, you had basically nanojoule pulses at 100 megahertz, which is 100 milliwatt of average power. And when you do measurements, you're always, a signal to noise is limited by average photon flux. When you take a 1 nanojoule pulse in the attosecond domain, it typically, because you need this really high intensity to create the attosecond pulse, these pulses come at a kilohertz. So your average power is a microwatt. So you have already 5 orders of magnitude less signal to noise. And that's why there is hardly any measurements done in the attosecond domain, which is pump and probe. So that you take an attosecond pulse to start a process and probe at attosecond time resolution. So the first attosecond time measurements have been done actually with some kind of streaking technique. But you know, right now there's a huge amount of laser work going on to push the power, the average power up, so that we can get the nanojoule attosecond pulses at a megahertz. But that, of course, requires high average power. So there is work going with amplifiers that normally, traditionally, the amplifier, this is the pulse energy as a function of repetition rate. Typically, amplifiers are at a kilohertz or lower pulse repetition rate. And, you know, there is a lot of work going to push the amplifiers into the megahertz regime. But if you push the repetition rate, then you go into the average power. You go into hundreds of watt or even 1,000 watt of average power, right? This is where the money comes in. And at the same time, you know, for example, in my group, we're pushing the average, we're starting with laser oscillator, and we're pushing the average power of laser oscillators into the hundreds of watt kilowatt regime, so that the short pulses directly come out of a laser. And I mean, and because of that, we then can ultimately do, hopefully, this attosecond pump and probe. But meanwhile, you know, we do this streaking. so because these attosecond pulses have one advantage, they're synchronized to the infrared pulse, right? And so the first measurements have been done by using the attosecond pulse, which is much shorter than an optical period. Remember, this is 2.7 femtosecond. You have synchronized to the attosecond pulse an infrared pulse. And the infrared pulse is very well defined. So depending on the timing when the electron comes out of whatever you're going to look at, it will be amplified by the electric field of this infrared pulse. So you map ionization time to final energy, right? So it's a streaking of this electrical field depending on when the electron comes out. So you map time to energy. This is the so-called streaking technique. In the Otto clock, I'm using actually circular polarized light. And we know in a circular polarized light, the electric field rotates in one optical cycle all around 360 degrees C. So in one optical cycle, which is in the range of a femtosecond, the electric field goes in full rotation. And we know we can do time, like a stopwatch, we can do time measurements when we have this rotating electric field. The time accuracy is better the faster the hand of the clock is moving. So you know the hour hand, the minute hand, the second hand, and you make more and more accurate measurement. And for example, if you work at a center wavelength of 735 nanometer, as I've been using it in the Otto clock, you know, 1 degree equals to 7 attosecond. So you have a perfect attosecond time resolution if you angularly resolve your dynamics. And this was the principle of the Otto clock, how we resolve then the tunneling delay, which will be the topic tomorrow in more details. So this is just to give you a little bit of flavor why we care about short pulses and what we can measure. And the nice thing, what makes actually ultrafast laser physics so exciting is that it's a very interdisciplinary approach. So you learn the technology, then you can apply it to engineering, to biology, to chemistry, to physics. You can go anywhere you want with this if you know the technology. And this is what makes it so absolutely interesting. It's never going to get boring because there is always some open question in some kind of a field that needs to be resolved. And you can use the same kind of techniques, right? And that's why I think ultrafast science, you know, when you do a PhD and then you move on, and you can do a PhD in physics and then move on to biology or whatever, right? That makes it actually so interesting and so rich. So now let me go into the more detail, basically the lecture 2. Where are we time-wise? Okay, we are now at basically I can keep going a little bit more and then we'll take a break. So it's important that you understand some of the basics. So far I've been pretty general. Was it okay? Was it all known or was it okay? So you have a feeling, right? Now, of course, we need to start understanding the pulses better. So the topic of this second lecture in a little bit more details is about the laser pulse and the frequency cone, okay? So I want to go a little bit in more details about this laser pulse. So you already got used to the idea that you can describe this laser pulse with a fast oscillating electrical field, which is the same electrical field like in a plane wave, right, which has this optical period. And you just have a pulse envelope that limits the flash of light, the laser pulse, into duration. So mathematically, you can write it in a fixed position as a pulse envelope A of t times I e omega naught t, right? Okay, A can be complex, doesn't need to be real. So normally, very often you normalize A of t such so that the magnitude squared gives you the pulse intensity, right? So let's take an example, a Gaussian pulse shape. Because, you know, for many experiments, it matters what exactly the pulse envelope it looks like, right? So out of a mode-locked laser, you either get typically a Gaussian or a secant hyperbolic square, but I'll come back to it. Gaussian is very often a good approximation. People do all kind of approximation of pulse shapes in their calculus, but it makes a difference sometimes. So when we talk about a Gauss pulse, then the envelope is given by a Gauss function, e to the minus gamma t squared, right? And the gamma can be complex. So if you have a complex gamma, the real part of that one gives you can do that easy, this calculation, gives you the pulse duration. And normally in a laser pulse, the pulse duration, if nothing is said, the pulse duration is always full width half maximum. That's a convention. And people sometimes are a little bit sloppy, don't say it anymore. Full width half maximum is the pulse duration. So basically it is the intensity from the intensity full width half maximum this is the pulse duration, tau p, when people talking about it, right? This isn't the convention. Like you have on a Gaussian beam, that the radius is the e to the minus 2, right? This is our conventions. And then the complex term will have here then an additional time-dependent phase shift here on your laser pulse. And that gives you a time-dependent frequency, right? Because if you have a time-dependent phase shift, you can define a momentum frequency if you take the first derivative. If gamma 2 is 0, then you will just end up with omega naught. And if gamma 2 has a certain value, then you get a time-dependent frequency. People always say, oh, time-dependent frequency, either you're in the time domain or a frequency domain. What about the time-dependent frequency? Oh, I'm blacking out, right? You know, take a car on a road coming by me. It makes, that's a pulse, an acoustic pulse with a time-dependent frequency. It's not a linear chirp, because it might, you know, that's a Doppler shift, right? By the car going by, that's a time-dependent frequency. A bird that goes, time-dependent frequency. Music, time-dependent frequency. Okay? So it's actually everywhere. So just relax, right? It happens. And so what does this mean to the laser pulse? What does this mean now with this time-dependent frequency? The time-dependent frequency means that the oscillations here that are equally spaced when gamma 2 is 0, so that you don't have a time dependence in the frequency, then each period, each distance of these oscillations is the same. So every position inside the pulse, you have the same spectrum, the same center frequency. But if you have a chirp, a time-dependent frequency, basically means that this period is changing over time, right? So when you look at the laser pulse, what is the spectrum of the laser pulse? Because we need to know about the spectrum. So we know you can do the Fourier transformation to get the spectrum. The Fourier transformation is clear. So you take that the electric field as a function of t is basically the superposition of the different waves at the specific frequency added over the full spectrum, right? E of omega versus tilde here is my spectrum of this laser pulse. So what's the spectrum of the pulse envelope? Mathematically, you can show that the spectrum of the envelope can be described by this expression, where delta omega is the difference to the center frequency. So if you look at this, you can easily show, if you do this equation, it's a one-line proof that this is the case. So if you have the optical spectrum of your pulse, it's centered around omega naught. In a Gaussian pulse, you have a Gaussian spectrum because the Fourier transform of a Gaussian is a Gaussian, right? So you have a Gaussian spectrum with a certain width. Normally, the full width half maximum of an optical spectrum is again defined with the intensity of the spectrum, the spectral intensity, full width half maximum. And you can easily show now, when you look at this equation here, you can write it as omega naught plus delta omega, then pull out here the omega naught. Then you have here the spectrum of your pulse envelope. So you can easily see that the spectrum of the pulse envelope is the same as the spectrum from the electric field pulse, but shifted to 0. So the whole information about the pulse form, the slowly varying pulse form in contrast to the fast oscillation here, is actually given by the form of the spectrum, and it's basically in the pulse envelope, right? It's very easy. So this is something you really need to remember. The spectrum of the pulse envelope, the same as the electric field, just shifted to DC by the center frequency omega 0, right? So you can then easily go through the mathematics. So we looked at the Gaussian pulse shape, but you can also get other pulse shape like secant hyperbolic square, which is basically the so-called soliton pulse. In comparison to the Gauss pulse, it's very similar to the Gauss pulse. It's just a little bit, it normally has more wings. So if this is the Gauss, you know, the soliton pulse is has a little bit more wings. Okay, not so nice. But what is interesting when you then look at the full width half maximum of the optical spectrum and the full width half maximum of the pulse, you have a so-called time bandwidth product, right? This depends on the pulse shape. So for a Gaussian pulse, you have a time bandwidth product of 0.44. For a hyperbolic secant, it's 0.31. Okay? So meaning the spectrum here, the spectral width is basically the product is 0.44. If you look at the spectrum for a given pulse duration, it depends a little bit how wide the spectrum is, right? So these are numbers for anybody who is working in laser physics. We know these numbers by heart, right? Secant hyperbolic, what this time bandwidth product is. So what happens now when I send this pulse through dispersion, through a medium? What happens? You have dispersion. So normally in a material you have certain absorption. And if you look at the refractive index over Kramer's chronic, you have a connection to the refractive index, right? So at lower frequency, normally your refractive index is larger. And then if you move above and above and above all absorption lines, you ultimately go to 1, right? Refractive index 1. So in the hard X-ray, you asymptotically, slowly but surely moving to 1, with actually a refractive index slightly below 1. Right, slowly moving to 1. And we are normally, with our infrared and optical spectrum, we're somewhere in between these absorption lines. So normally, you know, we have the terahertz absorption, these are the phonons. And then we have the electron absorption, which are in the UV. And we are in the infrared and in the visible, we're in between. And when we use glass, we are in the transparent regime, and typically in this regime we have so-called positive dispersion, which is also called as normal dispersion. And basically means the curvature of the refractive index as a function of frequency, the second derivative, the curvature is positive. So the positive dispersion regime is defined by this expression. It's the second derivative, Why do you care about the second derivative and not the first derivative? It's because for the pulse broadening, how the pulse shape is changing, the first derivative is irrelevant. The first derivative is only giving you a pulse delay, but never a broadening. And that's something which is intuitively, when you ask people, that's not obvious. But you can go through the math and show it. And for a Gaussian pulse, you can actually go through the math very carefully. So what happens, if you take a so-called transform limited pulse, a transform limited pulse means you have the shortest pulse for a given spectrum. When you have the shortest pulse for a given spectrum, then you have an unchirped pulse. That means that you have nicely equal distance between all the oscillations. And then if you send this transform limited pulse through a dispersive medium, then the different frequency components of this pulse will get different phase shift, right? And what actually happens is you get a chirped pulse coming out. Different components in your pulse will get different delays here. And in the normal dispersion regime, it is so that the blue comes first and the red comes later in the positive dispersion regime. And so when you do, how do you calculate the propagation of a pulse? You take the E of t, you make a Fourier transform, and how is this spectrum propagating? It's very easy. It's E of omega times e to the minus kn of omega times z, right? It's a plane. It's because each plane wave component is propagating like a plane wave. Because remember, the notation in laser physics, if you go to quantum mechanics, you have a different notation. But in laser physics, you use the electrical engineering notation for plane wave, right? So you have plus I omega naught propagating in positive z direction. That means, you know, if you take an equation out of the laser physics books, you have to be aware that they normally use this notation. If you take an equation out of the quantum mechanics book, they use the other. Matters sometimes, right? It's just a sign. So if you take the Fourier transform, you let it propagate with this phase shift, and then you make a Fourier back transformation, and it gives you then the pulse. This is the input pulse, and then you make a Fourier back transformation, and then you have the pulse that is coming out, and you can easily numerically calculate it. If you want to do it analytically, you basically do a Taylor expansion of the dispersion. So you take your Kn, so the Kn is the wave vector 2 pi over lambda, right, which is perpendicular on the wavefronts, and is basically Kn in the notation always is K times N, and this is the 2 pi over lambda, where lambda is the vacuum wavelength, right? So you then make a Taylor expansion of this one, the first derivative, Kn d omega times them, then and so on. And so you take the first order dispersion is the first derivative, second order dispersion is the second, and so on. That's the typical notation that people use, right? And so if you then do this Taylor expansion, you can actually go through, analytically go through this Fourier back transformation in the slowly varying envelope approximation, which I not have the time to explain. But you can actually analytically derive what the pulse looks like. So you put in a Gaussian pulse at the distance z equals 0 and let it propagate, do all this Fourier transformation analytically with Taylor expansion up to the second order. And this is what comes out. And you can see then that basically the pulse envelope is propagating with the so-called group velocity, and out of this calculation comes that the group velocity is given by d omega derivative dkn, and because normally in materials people give this, the dispersion n as a function of omega or n as a function of lambda, it is easier to calculate the group velocity as 1 over dkn d omega, which is this first derivative of the refractive index, right? So this is the group velocity, and you can see here the phase fronts here from the electric field. They are propagating with the so-called phase velocity, and the phase velocity coming out of this calculation, which is a couple of pages, right? You have to go through all this math, is omega over kn. And it's clear this is not the same in a dispersive medium, right? So the phase velocity, that's the speed at which these fast oscillating electric fields are propagating, is different than the pulse envelope. You know that also in waves on lakes, right? If you go very early on in the morning on a lake and throw a stone in it, you can actually see how the wave fronts come faster towards you than the whole wave mountain, right? The block of wave, the wave packet. The wave packet as a whole moves slower than the wave front. So even on water, you have this difference in the phase velocity and the group velocity. So this is very, very important, okay? So that you have these two different velocities. And I think from a notation point of view, it's easy. This is the group, it's the wave packet, it's the pulse envelope, it's the whole group. The energy is propagating with the group velocity. So normally, the material properties are given by the so-called Sellmeier fits. There is whole short catalogs. I mean, by now it's all on the web. You get the refractive index as a function of wavelengths. And you can actually show, this is a very useful table. You can calculate basically the phase velocity as a function of the wavelength-dependent refractive index is C over n. The group velocity, it takes a little bit of math to prove these two things, but it's nothing miraculous. You know, you have to take into account that K is also omega dependent and N is omega dependent. So you have to go through this properly, and then you can show that this is the same, right, as a function of the lambda definite. So, and then the group delay is the time it takes for the pulse to propagate over the distance z with the group velocity, z over Vg is the group delay. And you can see here, this is the first derivative of the phase that you accumulate. The phase is always knz, right? So this is the dispersion, first order is the group delay. And then you have all the other terms, the second and third order, where are they coming in? You can show that they actually coming in the pulse lengths. So you get this regrouping of the frequency component in the pulse, and the pulse length after a certain distance is given by the second dispersion. So only the second order of dispersion gives you a pulse change, and higher, of course, right? The third, the fourth, and so on. The broader your spectrum, right? Yeah?
How is this affecting the coherence?
Yeah, so far everything is coherent. We're not destroying the coherence because all the spectral components are in phase. We don't create any additional noise. You know, if I would create additional phase noise here, which would be not a coherent superposition of all this spectrum, then I would just create noise, right? So, no. Everything is coherent at this point, right? Everything, because it's the superposition of each spectral component, and they are all have a defined phase, And then while they're propagating, they have only the phase difference because of the propagation. And then you can actually show a good value to know if you, because in the lab you need to say, so you're working with picosecond pulses, you're working with femtosecond pulses. Can you send a 10 femtosecond pulse through a focusing lens? If you want to do an experiment and ultimately want to focus, you need to quickly check in the lab, can I send it through a lens? Do I need to take actually this pulse broadening into account? So now I worked so much, invested so much money, got a 10 femtosecond laser in my lab, and I now want to do an experiment, a pump probe experiment, and focus the light into my target. Can I use a lens? Or can I send it through a fiber? What happens with the pulse? So I quickly need to check if this is okay. And you can easily show that this more complicated dependence here can be actually in the regime if this pulse broadening becomes important, meaning that the dispersion second order is much larger than the initial pulse duration, then the final pulse duration is the dispersion second order times the optical spectrum. Now let me give you an example. Okay, but one more important thing, and then we'll take a break, I think. Let me see. Yeah, then it's time. And during the break, you think about it. Please remember, dispersion is a linear process, is a linear pulse propagation, meaning only the pulse in the time domain gets broadened. The spectrum remains the same. The spectrum is unchanged. You can prove that with a single line, with things that are standing here in front of you, and you think about it during your coffee, and it's very easy to explain why the spectrum is not changing in dispersive pulse propagation. And therefore, dispersion pulse propagation is linear, which means when it's linear, you can always regroup. Right? You broaden, this is the whole idea about chirp pulse amplification. You broaden your pulse and then you bring it together. The coherence is always maintained, right? So you always just regroup the different components. Mm-hmm. Right. Because, you only get a phase shift, right? And the intensity of the spectrum will not change. It's only a phase shift. It's also, when you actually send a pulse through a fiber and the input spectrum and the output spectrum after the fiber is the same, you actually pretty much know you are in a linear pulse propagation regime, except if things just compensate each other. So it's a good check, right? Okay, now let's get a little bit of numbers, because it always helps. Certain numbers you need to have in the lab to get a feeling, right? So let's look at, for example, fused quartz. So this is a typical material, fibers, a focusing lens, a glass, everything is kind of in the same order of magnitude. So fused quartz refractive index at 0.8 micrometer Ti-sapphire laser wavelengths is 1.45. When I look at the first and the second derivative, I can calculate this out of the Sellmeier equation and then calculate the first and the second dispersion order with this table that I showed you, right? This gives you then the first and the second order of dispersion over a certain distance set, right? So you can easily calculate that. So for fused quartz at 800 nanometer, you have the second dispersion order is 36 femtosecond square per millimeter. Okay. Now, assuming you go through 1 millimeter of fused quartz, your second order dispersion is 36 femtosecond. That means if your input pulse is 6 femtosecond, squared is 36 femtosecond, you are kind of just getting into the regime where dispersion pulse broadening becomes important, right? You want to have that this strong pulse broadening occurs when the dispersion second order is much larger than the input pulse duration squared. So what happens if you send it through more than 1 millimeter of fused quartz? You know, until you get normally on your device, on the test, on your experiment, you may use a couple of focusing lenses, and the focusing lenses are thicker than 1 millimeter, right? So assuming you invested a lot of money into a 10 femtosecond pulse laser system, and you go through a couple of 1 centimeter of fused quartz, couple of lenses, then you're actually at the end, after all these lenses, after 1 centimeter, so you get a pulse broadening of a factor of 10. So at the end, at your experiment, you actually have 100 femtosecond pulse. So your whole time resolution is gone, right? If you actually would have gotten a cheaper 100 femtosecond pulse to begin with and send it through 1 centimeter of fused quartz, nothing would have happened. You will still have the 100 femtosecond, right? No pulse broadening for the 100 femtosecond. So an easy way, an easy estimate, does it matter when I go through stuff, is this number. Fused quartz, 800 nanometers, 36 femtosecond square per millimeter. And you have strong pulse broadening if you're going through materials so that basically the 36 times the length of all your dispersive medium is much larger than the input pulse duration squared. It's important to realize that this formula is only valid for an input transform limited pulse, right? A dispersive pulse broadening does not change anything on the spectrum. That doesn't mean that if you go through a few 1 centimeter fused quartz, then your pulse is 100 femtosecond, then you say, oh yeah, and now it doesn't matter. I keep sending it through everything, nothing happens. It is the spectrum that does your pulse broadening, right? This formula is valid for an input transform limited pulse because the pulse broadening is given by your spectrum. You understand what I'm saying? So if you send it your 10 femtosecond pulse through 1 centimeter of fused quartz, you say, okay, pulse broadening to 100 femtosecond. Okay, now I have 100 femtosecond. Now send it again through 1 centimeter of fused quartz. Nothing happens, so it remains 100 femtosecond. No, 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 no. Because, you know, if you go through 10 centimeter at the end, you have basically a picosecond. It's the spectrum. It's the same, right? So the pulse broadening is given by the dispersion second order, which is becoming more and more and more the through material you go, times the spectrum, which remains the same for a 10 femtosecond pulse. If you go to 100 femtosecond pulse, your spectrum is much narrower. A transform limited 100 femtosecond pulse, right? But you get a chirped one through dispersion, right? So this gives you a little bit a feeling how strong dispersive pulse broadening is. And you know, you can easily get now commercial laser on the table, very tiny, where we had to work very hard, you know, and you get your 5 femtosecond pulse in the laser. And you need to know that you need to be careful, and that's why you normally never use glass lenses, you use reflective lenses, so that you don't have this pulse broadening in the focusing. Okay, now, how do you produce the short pulses? Let me give you a little bit of an introduction into modelocking. The short pulses are produced with lasers, and the technique is called modelocking, and it goes back to the simple argument that if you, in a laser, I hope you all had your basic laser already, right? This is a graduate course. So I assume you had laser physics, and you know that the laser has axial modes. Assuming the laser lasers in many axial modes with arbitrary intensity distribution, arbitrary phase, if you Fourier transform that, you just have noise, right? It's not coherent. And if you, however, take all your axial modes and give it a reasonable intensity distribution and a constant phase, and if you Fourier transform that, you get a short pulse, right? Basically, 1 over the spectral width, the time bandwidth product of the pulse. Now, how do you do that? Normally, you do it through either active or passive mode locking. So the time domain picture is very easy to understand, right? So you have a laser with a resonator, you have an amplification and a loss, and you assume now you have a loss modulation. The loss is all the way actually in principle at the end of the standing wave, and per round trip you go through this sinusoidal loss modulation, and so the loss modulation you only get over gain, saturated gain, for a short time window, and so you obviously only get lasing for a short time window. So if you have this loss modulation and you saturate this gain, which is pretty low, so you have just this saturated gain in a solid state laser and a net gain window that gives you the short pulses. Now, how is that fitting? Why is this called mode locking? How is this now connected to the mode? You know what a sinusoidal loss modulator does, right? A sinusoidal loss modulator, you can write this mathematically as a modulation depth times 1 minus cosinus omega mt, the modulation frequency. So if you send a pulse through this loss modulator, you multiply it with this loss modulation in the time domain. If you do go into the frequency domain, a multiplication goes into a convolution, okay? And the Fourier transform of, for example, just one axial mode, which is a plane wave, gives you a delta. The Fourier transform of 1 minus cosinus gives you 2 sidebands at the modulation frequency. If you convolute this, you produce sidebands around the center frequency. So you push energy from your CW center frequency to the side bands at minus omega m and plus omega m. And if this difference is exactly the axial mode spacing, you basically, with this loss modulator, push energy into the other axial modes. So you push coherent, this is a coherent process, so you push coherent laser light into these axial modes. And it's like in section seeding, and you build up this whole frequency comb. Every time this one goes then through the loss modulator, you again push sidebands, and that's how you build up over many round trip this broad spectrum. And that's why it's mode locking, because it's a coherent process, they're in phase, and it gives you the short pulse. Yeah? Yes, it's different from Q switching. I will come back to this one. Q switching is definitely totally different. This is a totally coherent process from pulse to pulse. You know, and I'll discuss in the next lecture a little bit the differences to the Q switching. Normally, you don't get the short pulses with Q switching because Q switch pulses are always longer than the cavity round trip pulse, round trip time. And here, you know, in the laser, the cavity round trip time is in the nanoseconds.
So it depends on your modulation.
Yeah, here you basically, to get a short pulse, you modulate at the round trip frequency of your laser. So you always modulate so that this modulation frequency is covering the axial mode spacing, right? Which is 1 over the round trip time of the laser. Okay, so you modulate at 1 over the round trip and you build up this whole frequency comb, and the whole process is coherent. This is kind of a quick, simple picture. Now, you know, when you then go through this build-up phase, I mean, of course, you can show this all mathematical, but it's good if you could build up a feeling for it before you go dig into the mathematics. And you know, and my lecture normally goes over a whole semester and not just one evening. So all I want to get to you is right now a feeling. right, for this whole process. So basically, when this pulse goes through the gain and the loss is this sinusoidal modulation. So as during the build-up time, in the time domain, your pulse becomes shorter because you have this loss modulation, which basically makes the pulse shorter, right? You have this transmission through the pulse. It basically drives the pulse to become shorter. And then it goes through the gain. The gain has a finite spectrum in the frequency domain, and your short pulse has a finite spectral width, but the peak of your spectrum will get more gain than the wings. Therefore, when you go through the gain, you get gain narrowing. What does gain narrowing mean? The pulse gets wider again. Then it goes through the loss. The loss modulator pushes it together. The gain pushes it out. Chung, 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 chung. And at the end, you have a steady state. And normally at steady state, this fluctuation in the pulse is very minor. It's small effects at the end. Where in the build-up phase, things are stronger. It's breathing heavier. And then, and at the end, you have a balance, right? At the end is the pulse shortening through the loss is compensated by the pulse broadening in the gain. And that's your steady state solution, right? Yeah. Build-up time. The build-up time depends on the laser, but for example, in solid-state lasers, the modelocking build-up time can be even. I mean, normally you would like to keep it below a microsecond because otherwise it's not self-starting. So lasers tend to be less stable when the build-up time takes too long. So normally when you switch on a laser, just to go into CW lasing is nanoseconds, but the modelocking build-up time takes longer, because you have this breathing and then you ultimately go into steady state. So normally faster than a microsecond. When it gets longer, it becomes hard. So, and now you understand when I do passive modelocking, I can actually get a loss mechanism which is much faster than the sinusoidal loss modulation that I normally do in active modelocking. In active modelocking, I use like an acousto-optic loss modulator that goes at the round trip time. So it's a sinusoidal loss modulation. But with a Saturable absorber, and I'll give you an example afterwards, you can get much faster curvatures. I mean, much stronger curvatures here. And so from the time domain, it's very clear that you have a net gain window that is shorter, that gives you shorter pulses. But with this simple picture of the pulse shortening, the stronger this curvature is, the stronger the loss modulation pushes the pulse shorter, right? Then this balance will come at a shorter pulse. So if I have a Saturable absorber which is producing a self-amplitude modulation, then you can get shorter pulses. And then the question is, how does it start? It starts from noise. Because a laser, you always have a little bit of noise, and then one noise spike starts this process and builds up.
But it's a subtle thing because you don't want to be too sensitive to noise. So
yes, it's a subtle thing. And that's why passive modelocking on solid-state laser hasn't happened for a long time, and people for a long time were thinking it's not possible. Exactly because of this thing. At one point you want to get it started out of noise, but you don't want to have it too noisy that the whole thing explodes. It's a nonlinear process. And it's only a window over which it's actually self-starting and stable. And that's exactly the key. And that's why, for a long time, actually, these diode-pumped solid-state lasers have not been passively mode-locked. There was even the prediction that it can't be done when I was a graduate student. Right? So,
Another question. And could you please explain why, in this case, we have only one pulse per round trip? Why it doesn't go faster?
Okay. So normally, when you have an active mode locker, you have a sinusoidal active MOS, so you only force it to one. And here, you need to adjust your nonlinearity such that it only happens a pulse. Because for a given average power, if you have only one pulse per round trip, you have the most energy. And so you have to adjust your nonlinearity such that it is favorable that the laser has the lowest losses with only one pulse. And if it can get lower losses with 2 pulses, it will go in 2 pulses. That's exactly the point. The laser will always go into the state of lowest loss. And if this nonlinear element allows it to have lower loss with multiple pulses, it will go into multiple pulses. And you need to prevent that also. These are all these nonlinear mechanisms that you need to prevent, and that's why when you go into a passive mechanism, you need to adjust all the parameters correctly to prevent that from happening. That it explodes, that it's you need to have it self-starting, not going into instabilities, Q-switching instabilities, and multiple pulsing instabilities. And there's a golden window. So I give you one example of such a Saturable absorber. Most of you had basic semiconductor physics, right? As a physicist, you had it. So you know energy and the density of state. So in a bulk semiconductor, you have the valence band with the holes and the conduction band with the electrons. So if you have laser light, which is basically allowing a direct transition from an electron from the valence band to go into the conduction band, then you push electrons from the valence band into the conduction band over the full spectrum of the pulse. These electrons in the conduction band, and if you do this very strongly, it fills up all the states up here. That means if all the states are occupied, band filling, you will have no more absorption. So the absorption goes down because you fill up the states. And then these electrons here will scatter, electron-electron scatter, will thermalize through phonons, and will get a nice Palliot-Dirac statistic, which lowers the number of electrons. This is the intraband thermalization. This has been studied nicely in the 70s and 80s in semiconductor. This intraband thermalization, depending on where you go, how far you go in the conduction band, and the curvature and so on, is in the order of 100 femtosecond. And then, so it gives you initially a reduction of your absorption, which can be very fast. And then you ultimately have recombination, removing the electrons again. And in a good semiconductor, the electrons live for a nanosecond, really long, right? So if you, so this will give you a long, long tail. But very often, you know, this is so fast because this is already happening. If you, for example, if you have a picosecond pulse, this thermalization will already happening when you pump this up. So this will not give you a very strong modulation. So everything is given by actually the recombination, but the nanosecond is too slow. This is a really slow modulation, but you want to have a fast modulation to get the short pulses. How do you make it fast? If you introduce mid-gap traps, for example, low temperature grown gallium arsenide are being used for electronics. You know, they don't have the oxide. Like in silicon electronics, they have the oxide as an insulating material. So the low temperature grown, MBE grown material in gallium arsenide have been used as isolating materials. And they actually have mid-gap traps. And they make the electron disappear from the conduction band and therefore make this recovery so that the absorption much, much faster. And so by actually doing material growth parameter, how you grow it, what material you take, you can actually design your modulation. You can actually design your response here, how the Saturable absorber is working. And if you know semiconductor physics, you can dial it in. And, you know, that's why the semiconductor Saturable absorbers have been so successful, and I will then in the lectures, in the third lecture, go a little bit more into the detail of that one. You know, that was actually then the semiconductor Saturable absorber mirror, the SESAM, that then mode-locked the diode-pumped solid-state laser for the first time stably, without any instability and self-starting, because we could dial in all these parameters very carefully. And that's why they have been so successful. Now, let me go, before we go into the detail of these Saturable absorber, let me go into the frequency comb, because this is also another one where people. So when I say to you, a single pulse has a continuous spectrum, but a pulse train has a frequency comb spectrum. Does this make sense to you? Let me repeat again. A single optical pulse has a continuous spectrum. You saw it. The Fourier transform of a Gaussian gives a Gaussian, right? Continuous. But a pulse train gives you a comb. Now let me show that mathematically and in a picture right now. So when I talk about a pulse train, means that because out of a mode-locked laser, every round trip a pulse comes out, right? So I have basically a pulse E of t repeated at every round trip time coming out of this laser. The round trip time TR 1 over the pulse repetition rate, coming this short pulse, okay? And the pulse duration of the short pulse is given by the optical spectrum. Depending on the pulse shape, the delta spectrum width times the pulse duration is 0.44 or 0.31 or whatever, right? So assuming this is a transform limited pulse, constant phase over the pulse duration, but repeated at every round trip time. How do I write this mathematically? I can very nicely write this by this following notation. This is actually in Sigmund's book. That's how I learned it when I was a graduate student, actually. Before frequency combs with that notation have been invented. So you have actually, you know what a delta function is, right? It's one peak, infinitely high, infinitely narrow at delta function. It's a distribution, but we call it function. So if we have now a pulse train repeated, so it's a infinitely narrow, this is a delta comb, right? You add a delta peak at multiples of the round trip time, right? So this is your pulse train, but this pulse with the delta peak is infinitely narrow and infinitely wide. So if you then convolute this with a pulse, the way we discussed it, then you get actually a pulse repeated at every round trip, right? Can you follow this? So this is how you write mathematically a pulse train. This is actually some of the most useful thing, because that's how you can actually so easily describe how frequency comb are stabilized and so on. Everything, the whole Nobel Prize, how you do it is one line. Okay, also, let's go through this one. So the Fourier transform of a frequency comb is not a continuous spectrum, because of single pulse would be the green line, right? But because we are repeating this pulse, we end up with the frequency comb. But why? The Fourier transform goes with a convolution, goes into a multiplication. The delta comb, Fourier transformed, takes a little bit more effort, but it actually goes in also in the frequency domain into a delta comb. You can prove this one nicely. It takes a little bit more, so I'm not going to do this. But you can look it up in basic Fourier transform books. A delta comb in the time domain or in the frequency domain goes over in a delta comb in the Fourier transformation. And the spacing is then, when here the spacing is the round trip time, then this is the frequency comb with the spacing with the repetition rate. 1 over r is the repetition rate. And then multiplied So you have here basically the envelope of an infinitely frequency comb. Therefore, a pulse train produces you a spectrum which is not continuous but has a comb. Easy, right? Mathematically clear. It has to be like this, right? So that explains why when we look at the full spectrum from a mode-locked laser, you actually have the comb, the ruler in the frequency domain. Is it even constant when you have dispersion? So in a laser you have a gain, like an amplification. So is this comb even constant? If you have to take, if you get this pulse shorter and shorter and you have a really broad spectrum, is it equally spaced? What about the dispersion? What determines the mode spacing? Is it the phase velocity, the group velocity? So let's do a vote. What determines the spacing of the frequency comb from a mode-locked laser? Is it the phase velocity? Hands up. Why? Is it the group velocity? Hands up. Why? You have a 50% chance when you guess, right? Yeah, it's a pulse, but could you show it mathematically? What about the axial mode spacing? You can actually show mathematically. It's the group velocity. So, at steady state, the axial mode spacing, is you send the pulse through one round trip and the gain minus loss, so gain equal loss, and you have a phase shift for the pulse, which must be a multiple of 2 pi. The phase shift is this, again, the phase shift is 2 times Kn at whatever wavelengths times L, the length of the laser resonator, and that means it's a standing wave laser resonator. You go twice through the laser length, right? So this is the phase shift. So this should be multiple of 2 pi. And then the spacing would be pi, right? So delta lambda m plus 1 minus phi lambda m. Normally the axial mode spacing is pretty narrow, right? In a big laser like this, it's very narrow. So you can look at this as a first derivative times the spectral width. And if you take the first derivative of this phase shift here, you have the derivative of Kn in here. And that gives you the group velocity and not the phase velocity, right? So the spacing on this mode-locked laser, and visually it is like this, otherwise your laser would not be stable either, right? The pulse would not be a steady state solution going through a dispersive medium. So it's the group velocity. So you can even show it nicely mathematically. So it's a group velocity. Now, the frequency comb has basically, the repetition rate is given by the round trip time coming out, right, of this pulse train. Does it go to 0? Normally, not. Normally, a frequency comb has 2 things. What happens if it doesn't go to 0? Let me first maybe show you. Look. So normally, if you have a laser that is not stabilized, your pulse train has fluctuation in arrival time, which is the breathing of your comb, and you can have translation. These are the 2 degrees of freedom, right? Breathing and translation. Translation is by this offset, and this one is the breathing, right? So how to stabilize the repetition rate was actually already done in the 80s. Actually, my professor, where I did my PhD, he was one of the pioneers to stabilize the mode-locked pulse train with really low timing jitter. And how do you do that? you just put one of the mirrors in the laser resonator on a piezo and make sure that you adjust the cavity length such that the pulse repetition rate, which is just the round trip time, 1 over the round trip, is constant, right? So that's easy, adjusting that one. But how do you do the translation? What physical mechanism is the translation? You could stabilize it to an absolute frequency, right? But what is actually doing the translation? So let me go back. What is the translation? So, assuming there is an offset, FCO, I called it. But you know, why I called it like this, it's not because it's the chief executive officer. It has another reason, which comes out just in a little bit. So let's just say there is an offset in comparison to 0 of this whole frequency comb, which otherwise is equally spaced n times the f rep, right? So I can then write this pulse train with an additional offset instead of, so I'll take f now for frequency, right? F minus m repetition rate minus an offset. If I Fourier transform this one with an offset, I can actually take the shift theorem of the Fourier transform. What is the shift theorem of a Fourier transform? It gives you an exponential multiplication here. So this shifted thing will give an exponential component here. And of course, multiplication goes into convolution. So you have an additional time-dependent phase shift here of your pulse, which is the pulse envelope. This is normally your center frequency, omega 0. So this is the carrier, which omega 0 I call now the carrier, which is the center frequency, is the carrier in optical communication and so on. The carrier, because you modulate information onto the center, the carrier frequency. So omega c is the carrier. And then I have a time dependent. So I have a time dependent additional phase shift of this pulse through that, right? Through this offset. So what does this mean? It means that I have, the electric field has a different variation. Assuming here it's at maximum the electric field with the pulse envelope, but if I have a time-dependent phase shift, the electric field will not be all the time at the maximum with the envelope. That's why, and this one is the derivative here to this phase shift. But it's not continuous, it's per pulse. So it's basically the change of the phase from one pulse to over the time TR gives you the offset. And that's why we called it the carrier envelope offset frequency. So if I stabilize the translation of the frequency comb, I stabilize the electric field underneath the pulse envelope, which was actually the problem that I tried to solve at that time in the 80s. I wasn't in the frequency metrology. I wanted to solve that problem because we got shorter and shorter pulses, and we wanted to do, you know, think about it. If you have a laser pulse that goes with electric fields fluctuating every pulse when you have this 5 femtosecond pulse and you want to do high harmonic generation, right? It's a very highly nonlinear process. It matters if you have an electric field of this strength or of this strength. Otherwise, it's a noise generator. Right? Each pulse has another maximum electric field. It's total noise generation in nonlinear optics, extreme nonlinear optics. So we wanted to stabilize this one. So we realized, oh, this offset is actually related to this offset, to this translation. But then we still had the question, how do I measure this offset? So of course, if you have a very stabilized laser, somewhere as a reference, you can do the beating and stabilize it to an external frequency. But then you need an additional laser. You lock your mode-locked laser too, which costs money. There's a cheaper way. And actually, and also something also important, when you do the mode locking, you only you normally only have control over the pulse envelope, nothing on the electric field. The electric field is not stabilized in mode locking, only the pulse envelope. So normally out of a laser, each pulse has a different carrier envelope offset frequency, if you have it running. So, but you can actually control this one inside the laser, and it's actually any difference in the laser, any knob which is a difference between the phase and the group velocity can control the position of this one, right? Because this one is propagating with the phase velocity, and this one is the group velocity. So if I have a knob that allows me to adjust the group velocity and the phase velocity, I can make them always coming exactly the same way, as long as I can measure the carrier envelope offset frequency. But how can I measure the carrier envelope offset frequency? Here, without an additional reference. It's this one down here. Normally I don't have any signal down here. And I don't want to bring up another stabilized laser, which is really expensive. How do you do that? And a really clever way that we proposed, actually, in collaboration with Keller, was basically this F to 2F interferometer before Hensch and Hall, published 1999. That's the paper I gave you to read. So basically, if you have a very short pulse, which is covering more than an octave, then the frequency doubled spectrum of this pulse will have an overlap with this fundamental spectrum. So what is this overlap doing? Because this overlap is not perfectly overlapping with the fundamental when the CO is not 0. And you can show that with one line. And there is the whole invention. One line. Let me go you through the math, right? So this is your frequency comb. F1 CO plus N times F rep is the fundamental pulse. Then you frequency double the pulse. So it's 2F1, 2F is the blue one, right? Each stick. Now, when you look at then, if this is a more than an octave, and you take the higher frequency part of your fundamental pulse, which is at 2N F rep, so the F2 is the higher frequency part of your fundamental pulse, is CO plus 2N F rep, is this F2, and you beat it with the lower frequency part of your frequency doubled spectrum, you actually get a beat signal. If you just look at here on a photodetector, put it on a microwave spectrum analyzer, you see huge signal. This is the pulse repetition rate, and this is the CO frequency. So, and you can see that this is the beat, because if you take basically the 2F1 minus the F2, the 2F1 minus the F2 gives you the CO frequency. So as long as you have a spectrum that is covering more than an octave, so that the frequency doubled spectrum has an overlap with your fundamental, you can see it on a photodetector and spectrum analyzer. And if you can see it, you can stabilize it. It's kind of like, you know, if it bleeds, you can kill it, right? So, so there is some fundamental, because, you know, as an experimentalist, if you measure something, then you just turn knobs and try to understand what makes things change, right? And, you know, anything that changes the phase and the group velocity differently will change the CO, right? So actually what it turns out, when you actually modulate the pump laser a little bit, it will shift the CO. So you can actually watch on your RF spectrum analyzer when you change things, how this is jumping all over the place. And if it moves, you just figure it out. You don't always have to have a stabilization mechanism. You know, I told you for the repetition rate, you change the cavity length, right? But that also changes the CO, because in air you still have a little bit of dispersion, maybe negligible, difference between group and phase velocity in air, still a little bit. Also changes the CO. But then with the power, you can actually show that if you modulate the pump power, for example, on your laser, it changes the group and phase velocity differently than when you do the cavity length. So they are not independent knobs, but as it turns out, actually, you know, sometimes life is very nice to you. Actually, as it turned out for the solid-state lasers, I mean, many years later after we understand and so on, actually, it even helps you. So that there are not independent knobs, and at the end you can get it even more stable than if you would have had independent knobs. You know, it's complicated, but you know, believe me. Sometimes, you know, life is just good for you. You know, there are days where basically no matter what you do, it always gets worse. But there are days, no matter what you do, it always gets better, and you just enjoy it when it happens, right? This is one of them. First, you think this is it's a problem. Actually, it turns out if you do it right, it actually can be good. Most of the time, if you understand it, you can most of the time find an application that you actually even can use it and make it better. Electrical engineers, feedback loops, they're very clever. They can do it. Okay, so this is what we published in this paper. At that time, actually, we had the world record in Ti sapphire laser, and we didn't have an octave spanning spectrum. So we didn't have enough spectrum, enough signal to do this directly F to 2F, as it was later on. This was then called as the F to 2F interferometer, you know, F to 2F interferometer technique. Basically, we didn't have enough signal to get enough beat signal to noise on the beat signal, because you need about 30 dB to do a good feedback loop and stabilization mechanism. And so we came up with a whole bunch of different techniques how you can do it. You know, if you actually do frequency doubling and frequency tripling, you can actually work with narrower spectrum, for example. Once you understand this equation, you can come up with a whole bunch of other ones, right? Once you understand this. So that's what we actually showed in this paper, a whole bunch of different techniques where you needed different spectral width. Now what Telle and Hensch group did, they actually used the microstructure fiber. So what they realized is you don't really need the shortest pulses from the Ti sapphire laser. You can create a very broad supercontinuum with this microstructure fiber. You get white light out of this. But normally you always think when you have an extreme nonlinear process, you have a lot of AM to PM conversion, basically meaning intensity noise, producing a lot of phase noise. So this whole white light might not be not coherent. And it's true. You know, not all white light that you produce with a short pulse is coherent. But with the reasonably short Ti sapphire pulse, it is coherent. And actually, then you can use this one, then you have more than an octave of spectrum and can do this F to 2F beating and get this stabilization. What was amazing is actually that even though you produce this white light, how coherent it is. There is a little bit of noise, this is true. But it is amazing how little noise you produce. Again, something which you normally would think, poof, shouldn't work, but it works. This is the amazing things. So this whole, you know, what you can do today, you can actually stabilize the electric field underneath the pulse envelope. You need to do that. There are commercial products out there. You can even amplify these pulses, compress them, and they're still stable, which is pretty much amazing when you think about it, because any difference between group and phase velocity, so if you have fluctuation in the path lengths, or if you go through amplifier and compressors, you have to be a little bit careful how you do it, that you don't introduce differences, noise in this. Otherwise it creates noise. So this F to 2F interferometer uses basically pulse strain because it's built on this frequency comb idea. But in amplified pulses, very often your repetition rate is really low, so you deal with individual pulses and not with a lot of pulses coming. An individual pulse has a continuous spectrum. So how do you do it then? So if you have a very broad spectrum, a single has a continuous spectrum, you frequency double it, and if they are overlapping and the CO phase is not arbitrarily going in fluctuation mode, you actually, because the CO phase gives you an additional phase shift, right, in the carrier, then you can actually resolve the spectrum, the interference at the wings of the spectrum. If, remember, in the pulse, the CO goes, I know it gets a little bit late, but, remember, here, you see, here. If you have, this one is related to this CO phase. So if you have not a stabilized frequency COM, you have an arbitrary phase. And if you do an interference with an arbitrary noisy phase in there, you don't see interference, right? So that's why if you then do the frequency doubled and you have a stable, you only see interference if you actually have the CO phase stabilized. And so if you have single pulses, you see the interference at the overlap of the spectrum. If you have arbitrary free-running laser, you normally don't see interference. And so you can see nicely the interference fringes on each pulse stabilized or not, right? And that's how you use today these lasers to, oh my God, and we are only in lecture 2, basically to do the high harmonics. So you need those CO stabilized pulses to do the high harmonics and the attosecond pulses. Now, are you ready for until 12 o'clock or what? Yeah.
During the use of microfibers, so does the change also depends on the width and of the diameter of microfibers specifically? Because
this is a very good question. Under what condition is the supercontinuum generation coherent? There's a whole book written about this one because in these microstructure fibers there is a whole bunch of nonlinear processes starting. There is self-phase modulation, self-steepening, Raman, you name it. There is so many nonlinearities, and the amazing thing is that it's actually much longer coherent than you think. That's the amazing thing. But to really predict the coherence on this supercontinuum, you ultimately need to run the numerics. So John Dudley has one of these review paper written about that one, which I would encourage you to read. It's nonlinear pulse propagation. So far, we only did linear pulse propagation. So there's a whole lecture, on nonlinear pulse propagation, which we haven't really touched. So we would be here for a long time. Okay, lecture 3. So we're getting, let me.
How many slides do you have?
How long can you hold? How long can you go? Yeah, no, 5 minutes. Let me just give you a little bit of, because there was an earlier question about Q switching versus mode locking and so on. So, when you look at the different mode of operation in a laser, you can have it CW running, ideally in one axial mode, right? Continuous wave, one axial mode. Or then you can have it running in Q-switched, one axial mode Q-switched, multi-axial mode Q-switched, which normally causes a lot of noise, or Q-switched mode-locked or mode-locked. So we looked at this one now, CW mode-locked, right? So the Q-switching, normally I don't have the time to explain it to you how Q-switching is done, but the Q-switching is defined. You can get stable pulses, but if they're Q-switched, the pulse duration is always longer than the cavity round-trip time. Because as soon as it is shorter, it is repeated at the round-trip, and then it goes into the delta com and the whole thing, right? So the pulse duration is always longer than the than the cavity round trip time. So, either you make the laser really, really short, or otherwise forget about the short pulses. I mean, femtosecond is very hard to get with Q switching. And then mode locking, fundamental mode locking, you want to have 1 pulse per cavity round trip, right? And then the pulses are repeated at every round trip going through the output coupler. You can have situation, this is also stable, that you can have multiple pulses per cavity round trip, but most of the time you don't really want it, because then you need to make sure that then the pulses are really stable. In fundamental mode locking, it's stable. Either it stops mode locking, or then it's really only 1 pulse. In harmonic mode locking, you need to then stabilize these subharmonic pulses against each other, and otherwise they introduce noise. They will mix with each other, and this is not such a healthy situation. So normally you want to run your laser in fundamental mode locking. But depending on if you have a saturable absorber inside the laser, it can also go into Q-switched mode locking. And that's normally, if you are lucky, you have pulses, mode lock pulses, which are then strongly modulated, like in a Q-switching regime, slower than the round trip time. But this is normally also not something you want, because then each pulse is modulated, not each of them are the same. So for many applications, that is not desirable. So normally, you either want to go into single, stable, axial Q switching, but long pulses, or then CW mode locking. And the breakthrough for diode-pumped solid-state laser was really by introducing this SESAM, where I could adjust all the parameters correctly to make it self-starting, to prevent Q switching, to make only 1 pulse per cavity round trip. And this is because with the semiconductor, I could change a lot of things, all the parameters. You had the full control of all the things. And, and traditionally, people knew about diode-pumped solid-state laser, or they knew about semiconductor physics. And I was lucky at Bell Labs, after my PhD, I had access to semiconductors and diode-pumped solid-state laser. And it was, as usual, when you make a breakthrough, when you actually have an interdisciplinary effort. But I could now stand here, and it has been a success story. So I invented the first device I did in 1992. And I could say, oh, I was so smart and I knew everything. But the reality is, the most important breakthroughs are coming because you nearly stumble onto it. And by trying to understand something that maybe didn't even work out than what you wanted to do. So don't get too upset if your experiment doesn't work. Maybe you are at the edge of a major invention, right? So you need to understand why your experiment doesn't work, because that gives you normally a lot of ideas. I mean, this is actually how we invented the Otto clock. The experiment didn't work. So I could give you now a large lecture of how smart I was with this one, but I was lucky. I was in a lab with a lot of tools. I had a lot of equipment and the measurement tool, and I just stumbled on and was smart enough when I actually stumbled onto something I knew that this is maybe good, okay? And so I followed up on it. So I explained to you how with semiconductor saturable absorber you can get a custom designed recovery time. So you can actually custom design your modulation, your self-amplitude. But another important thing was, when you put this semiconductor saturable absorber on a mirror, right? Then as soon as you saturate the absorption, the reflectivity goes up and it will ultimately saturate. And at what pulse fluence this reflectivity starts to saturate, how strongly it saturates, which is the modulation depth, and how much residual losses you have, this all plays a role in your mode locking dynamics. And you need to adjust that right to make it work. And as it happened, the semiconductor was an ideal situation. and you know, you can get with semiconductor basically a SESAM at any wavelengths. But now let me give you a little bit of an idea how I stumbled onto it, how the idea evolved. Because, you know, it was really as a PhD student, I actually did a master's degree in physics. So when I nearly became a theoretical physicist. And then I went for my PhD to Stanford. And, you know, at the beginning, I didn't even know what a lock-in amplifier was. You know, I mean, I had no idea about measurement technique. And I ended up being with an electrical engineer as a professor. And when I joined his group, I didn't understand a single word. They talked about dB, and you know, the other PhD student said, "Oh, take the HP 8566." You know, they knew all the instruments by the number of the manufacturer, and I kind of was thinking, "Oh my God, I'm in nerd country to the power of 10." Okay, but I stuck it out. Okay, I learned dB, dBc, and all this stuff. Huh? And actually what I've learned with an electrical engineer as a PhD advisor, I learned measurement technique. I learned microwave technique. And that actually, these whole measurement tools and noise characterization helped me afterwards for every measurement I did afterwards in the lab. Where physicists didn't see a signal, I could see the signal. And if you see a signal, you can optimize it and stabilize it. No, it's true. When you see a signal, you can improve it. If you don't see a signal, you can turn whatever. You're blind, right? What I've learned with actually learning good electrical engineering education in experimental physics, I can tell you, this helps. Take some classes in electrical engineering. Because that basically made it for me to make a difference. And so, you know, basically, when I invented the SESAM, you know, it replaced all this active mode locking. So this was a typical active mode locker that I used for my PhD in the lab. It was an acoustic loss modulator, needed RF power, water cooling, and it was replaced by a SESAM, you know, and it did it all and even better. And that's, you know, the picture before and after, and that's why it was a success. Because it basically nobody does this anymore. Everybody does this. And that's why it was successful. It was much simpler, but the whole complexity went into the design of the SESAM. And over the years, I developed pretty simple guidelines, you know, how to design the SESAM so that it works. Okay? So, how did I invent it? When I became went to Bell Labs, the Ti-sapphire laser became a new material. And the new material is always good. Put your finger on new material, because that actually changes something. And certain things, people do certain things and keep repeating it without thinking why. But with a new material, their normal way of operation maybe just doesn't work anymore. And then you need to think, why doesn't it work not? Or maybe it works better. So everybody started to work on this Ti-sapphire laser, because this Ti-sapphire laser was finally replacing these dye lasers that produced before all these femtosecond. And the dye laser was a liquid laser. Who wants to work with a liquid laser that photodegraded? And if the jet was clogged up, you know, you got the dye all over you. So it was a messy situation, because, you know, everybody tells you, clean up the jet, right, before you go home. But, you know, like every graduate student or a young person, you forget it, and the next morning you switch it on, and then you have it all over you. So, anyway, Ti-sapphire is a solid-state crystal, much easier to use, was a great laser. And then there happened 2 experiments that actually should not have worked. And they worked. They were not mine. Okay? So the first one was a post-deadline paper by Siebert, where he demonstrated a post-deadline paper with a mode-locked Ti-sapphire laser without an absorber. Now, I told you, for mode-locking, you need a loss modulation. It had no visible loss modulation and produced 60 femtosecond pulses. Nobody knew how it worked. When we went to the post-deadline session, basically, you know, it was submitted as a post-deadline paper. It was afterwards on every fax machine in the world, and everybody had a copy of it, and we all went to the post-deadline session. It was standing room only to watch what is going on. Nobody knew what was going on, and it was called magic mode locking, because there was no Saturable absorber. People said, oh, there is a Saturable absorber in the Sapphire. Oh, there is something this, and oh, this is this, wild speculation. Actually, Siebert explained it in this paper with coupled cavity mode locking. And I explained to you why he came up with coupled, it wasn't the right explanation. The other one was another post-deadline paper, which also should not have worked. It was done by a Japanese group. They presented it as a post-deadline paper at Ultrafast Phenomena in the same year. And they basically built a so-called CPM dye sapphire laser. So all the femtosecond laser in the dye laser period were CPM dye lasers. And if you understand how they work, you never would build a CPM dye sapphire laser because they don't work. Because if you actually understand it, you don't build it. They obviously didn't understand it. Oh, now I'm on YouTube on this statement. Okay. Okay. Anyway, so they didn't understand it because they built it anyway, right? But it worked. It worked. But it should not have worked because, you know, when you know the CPM dye laser was a critical balance between the loss and the gain, and the loss was a very slow dye Saturable absorber that recovered in nanoseconds. How can you get femtosecond pulses with a loss modulation in nanoseconds? Slow. No way. It was actually an open net gain window in the dye sapphire laser. How could it work? Both were actually later on explained by Kerr mode locking. Both were fast Saturable absorber, and it was actually Kerr mode locking, right? And the Kerr mode locking, most of you understand by now. I don't have the time anymore to explain that one, because I want to go a little bit to give you a flavor why I came to the SESAM. So, coupled mode locking, right? I mean, Siebert explained actually his result with coupled moding. He said because the student had to slightly misalign the laser, and then suddenly, boom, it went into mode locking. And so they assumed it was a coupled cavity effect between the fundamental transverse mode and the higher order transverse mode. By the misalignment, you had a superposition of multiple transverse modes that were beating against each other. Because at that time, the big thing for solid state mode locking was coupled cavity mode locking. Because at that time, remember, it was said you cannot passively mode lock diode-pumped solid state laser without making them unstable. There was even a paper written by Hermann Haus who said it doesn't work. But there was this coupled cavity mode locking. Lynn Mollenauer became very famous in 1984 for mode locking a color center laser with a nonlinear coupled cavity. Basically, he had a fiber inside a coupled cavity, so you have your normal laser, no Saturable absorber, and you get here an effective nonlinearity that actually produces mode locking, because assuming you have a pulse here out of noise, and this pulse fulfills the soliton compression, the pulse gets shorter through the soliton effect, comes back, and gets a pulse shortening. So by going through this negative dispersive fiber, you actually, the pulse that comes out here comes back, gets soliton compression, gets sent back to the main cavity. It's kind of like a Saturable absorber. It produces a shorter pulse, like the loss modulation. Produces a shorter pulse that gets this balance, right? That ultimately makes this mode locking. So what actually Siebert did before he discovered this magic mode locking, actually one of his students took the wrong fiber one morning. Instead of a negative dispersion, a positive dispersion, it still worked. So instead of actually being a stupid student and actually saying, oops, I took the wrong one, replacing it real quick and put the right one in, actually the student realized, oops, this might be important, right? Because it still works. I have no clue why it works, but it works. So now think about it. Now that I had a very simple explanation. So with negative dispersion, I have soliton compression. With positive dispersion, you know, the pulse gets broader, coming back. So why should that make it mode locking? Doesn't make any sense, right? But it worked anyway. That's why we do experiments, right? Doesn't? So it was actually not really explained by the Sippert group. And actually it was that the group of Ippen and House who came up with a very simple explanation. They say, and they then introduced a new acronym and called it additive pulse mode locking, because you still have self-phase modulation. I didn't explain that to you. This is a nonlinear process. Basically, it takes the Kerr effect n2 times the intensity, right? So you take a self-phase modulation. So basically, if everything is adjusted right, you have a phase shift so that at the peak of the pulse, you have positive interference of the pulse coming back from the couple cavity and negative interference, destructive interference in the wings without this one. And so the superposition gives you a shorter pulse. That means you have to actively stabilize the cavity lengths here, because otherwise it wouldn't work, right? Otherwise you get arbitrary phase shift and you don't have this interference pulse shortening effect. And this is really true. This additive pulse mode locking only worked when you actually stabilize the cavity lengths. So, and then there was actually a theory paper that said any nonlinearity in a couple cavity should actually mode lock. A numerical study, right? No, you know, numerics, you can show a lot of things without getting a feeling, but they showed any nonlinearity. And here I was at Bell Labs. I had semiconductors. So instead of fiber, I put in semiconductor. I put in a semiconductor. So I borrowed a semiconductor mirror from a neighbor who used it for all optical switching, plugged it into the laser, and it worked. It worked even better than additive pulse mode locking because I didn't have to stabilize the cavity lengths, because I used an amplitude nonlinearity. And so by trying to understand why this thing actually works so well and so easily, I then came up with the SESAM, the first SESAM device. And actually the idea was, after I understood how it all works, you can take this coupled cavity and spatially move it on top of your other cavity, because this is the same length, and you put the same Saturable absorber, but put the output coupler, which was, I had like a 5% output coupler. So put a 95% top reflector on top of this semiconductor absorber. And I designed the device, got it grown, and it worked. And with this, I had a semiconductor Saturable absorber mirror, the first design. And after that, when it works, then you change parameters, right? Change this, and then you understand more and more how it all works. And that's how the SESAM was invented. Right? Yeah, so.
Did you have some serendipity with the recovery time?
Yes, because, you know, the funny thing is, I had, when I moved this one to 1 micron, I had actually, when I was growing it at normal temperature, the Saturable absorber, which means a slow recovery, then, because it was done at 1 micron, the semiconductor multiple quantum well section had surface roughness, and so it introduced scattering losses. And we solved these scattering losses by moving to low temperature growth. And the low temperature growth removed the scattering losses, but also made the absorber faster, and it all worked better on multiple levels. Solving one problem actually helped me on other ones. And then afterwards I realized, oops, that was actually good. And again, if you change parameters, so once you have an experiment going, change parameters and try to understand. You know, change things, and then you understand and make it better. And that's how it all evolved so that kept me busy for 20 years, and we're still publishing paper on SESAM design, because now we have SESAMs. Even, you know, at the beginning people were saying, oh, well, that's complicated. Or then somebody said, oh, it will burn. Now we have it in laser with over 300 watt of average output power. Inside the laser, 3 kilowatt with femtosecond, and it's not burning. Actually, the dispersive dielectric mirrors burn before the semiconductor. So this is the story. So, I mean, all I can say to you, I mean, I'm a hardcore experimentalist. I really like experiments, because we do experiments because we go beyond theory. Theory is always based on some assumption, and if you limit your assumption, you will always limit your results. If you go into the lab, you discover new things, because you're not limiting your assumption. You just have to make sure that you keep all your eyes open when you go into the lab, switch on all your detection, spectrum, time domain. The more you look, the more you see, the more you discover. And learn good measurement technique. Know what you are actually dealing with the instrument. Go a little bit over and learn something from electrical engineers, RF, microwave, signal to noise, generally good habit to know that you can make signals visible that normally other people don't see. Okay, with this I want to conclude. I hope you had a little bit of fun, and I hope I could get you excited for this field. And, you know, thanks for your patience, and, you know, see you tomorrow. Okay, thanks a lot.